we've been looking at the response of a single degree of freedom system to harmonic loading. We have seen how to look at the equilibrium, we have looked at what are the steady state forces. Then I started looking at transmissibility and I find that there are two ways of looking at transmissibility. One is where a force from a machine is transferred to the floor, and what we want to do is keep the floor forces as low as possible relative to the floor amplitude, floor force amplitude to a minimum as relative to the amplitude of the excitation force. Today what we are going to look at is we are going to look at the same problem which we call as and we look at the specific problem of the Bayes isolation. Okay. So, now the key point here to note is that when you look at force transmissibility, what kind of values did we get? Let us look at it. We got the transmissibility ratio, which was given as F T, the force transmitted to the floor upon the amplitude of the force, and this was equal to that was what we derived for the transmission of the force. And today what we are going to be looking at is we are going to be looking at the Bayes isolation problem. What was the Bayes isolation problem? The Bayes isolation problem was the following. Where you have a sensitive equipment connected through its foundation to a floor which is and automatically because of this starts vibrating, and what we want to do is the total acceleration. Okay. So, the total acceleration, the amplitude of the total acceleration, so I will call that as 0 divided by u g 0, this value is also another kind of transmissibility. Okay. So, this value we want to keep it to a minimum. Okay. So, let us see how to solve that particular problem, how to write down the equations of motion. And for this I will start off by looking at the acceleration transmission by looking at this particular. So, we have a rigid mass, it is being subjected to Bayes excitation. And we will call this excitation as a sinusoidal function, it is a harmonic function. Okay? I mean later on we will see that it does not really matter whether it is a harmonic function or not, we can still look at it, but right now let us look at it as this thing. So, if you look at this, okay, now this is going to be subjected to an acceleration, and this acceleration is going to be equal to given by m u into u double dot plus this is k, this is c. So, c u dot, which is the mass into the acceleration of this mass, okay, into the c of the relative velocity between the mass and the base. Okay. So, essentially what we have is the fact that the total acceleration is equal to the relative acceleration plus the ground acceleration. Because if you look at it, if the ground was steady and we looked at this, that would be the relative acceleration of this system. Okay. But since this is moving also, the mass is being subjected to not only its relative acceleration, it is also being subjected to the acceleration of the base. So, the mass does not know that the base is shifting, the mass only sees itself moving. What happens to the spring and the dashpot is that they only see the relative movement. So, in other words, u dot is actually velocity minus this, and u is equal to u total minus u g 0. So, in other words, these the spring and the dashpot see the relative motion, the mass however sees the total motion, and therefore, if you look at it, this is equal to this plus this, and there is no excitation on the mass. So, this is equal to 0. Now, the question then becomes is that how do we want to solve this problem? Okay. Now, there are various ways of solving this problem. Later on, we will see that we are really interested in the relative motion purely because we are going to be interested in the force in the spring. Okay. Right now, what are we interested in? We are interested in reducing the total acceleration that the mass sees. Okay. So, therefore, it is much easier to write the equation in terms of the total response rather than the relative response. Okay. So, if we write it in terms of relative, and putting this in, that u of t is equal to this into this, what we get is substituting this and this in here, what we get is m u double dot plus c u dot plus k u say u dot total plus k u is equal to c u dot g plus k u g. Okay. So, this is the solution that we get. Okay. And if you look at it, in other words, we can also say the following. We can look at it in this form. This problem can also be written as and note that u double dot is u plus this. So, this becomes u plus u g. So, if I take it on the other side, this becomes both these equations represent the motion of this. The only thing is that this is in terms of total displacements and these are in terms of relative motion. Total motion, relative motion. Now, the question then becomes is which is important. Since in this particular case, we are looking at specifically this problem of looking at u double dot t. Okay. Therefore, we are going to look at this problem. Okay. Now, however, what I am going to do is I am going to look at the solution of this equation, okay, and then say that look, m u double dot total is equal to minus cu dot minus ku dot. Okay, that is the way I am going to solve. So, I am not going to solve this equation. I am going to say that look, I am going to solve this equation. Okay. Note that this becomes something like this is the forcing function. Okay. So, if I have this as the forcing function, what is u of t? Well, it is very simple. This is a harmonic response. So, therefore, harmonic response we can always find it out, and look, note that this is a harmonic load. So, what is the response? Let us look at it. The equation becomes mu double dot plus cu dot plus ku is equal to minus mu double dot g sin omega bar t. Okay. So, now interestingly, what does this problem look like? This problem looks like this is the amplitude of the force, and this is a single degree of freedom subjected to a harmonic motion. What is the response to it? We have already know. Of course, only the steady state response. We are always looking at steady state response. Okay. Now, understand that I am done with boundary conditions and the transient way back. Okay. Right now, we always look at a situation where the load or the vibration has lasted for a long time, and we are looking at the response at this particular instant of time. This is how it normally is in real life. Okay. Because when you look at sinusoidal motion essentially comes from machinery, and machinery when they start, okay, it is a very different kind of a situation. It is when they reach the full motion, okay, that's when we are interested in, and that is like a steady state, because when it started was the initial condition, that does not come into the picture at all in this particular case. Okay. So, when I say u of t, I am always really looking at the steady state without explicitly stating its steady state. Okay. So, what is the response then? Well, it is f 0, this is f 0 upon k into d into sin omega bar t minus theta. Okay, where we know what theta is, we know what d is. I do not want to belabor the point. Okay. So, this is u of t. So, therefore, let me look at u dot of t. U dot of t is minus m u g upon k omega bar d cosine omega bar d minus theta. Okay. So, now let us look at this. So, in other words, we have got u dot and u, and all we have to find out is this. So, therefore, m u double dot becomes equal to minus cu dot. Okay. So, this is minus this. So, it becomes essentially m u g 0 upon k c omega bar d cosine omega bar t minus theta, right. Then minus k u. So, this will be minus this. So, this becomes plus again, plus m. K and k cancel each other out. So, this becomes this into. Okay. So, now we are going to divide throughout by m. Okay. If we divide throughout by m, what happens? We get the time history of our acceleration, total acceleration. So, the total time history turns out to be equal to u double dot total is equal to u g 0 c omega upon k into d cosine omega d minus theta plus u double dot g d sin omega t minus theta. Now, understand that we are not interested in the time domain of the response, we are interested in the amplitude. So, what is the amplitude? Note that this is a sine function, this is a cosine function. So, therefore, the amplitude becomes the following, and note what is this equal to? We know what this is equal to. This is equal to 2 xi beta. So, I am going to take u g 0 d outside. So, I got this into d, and inside I have, so therefore, 1 squared plus 2 xi beta squared square root, right. This squared plus this squared under root. So, since I take u g 0 outside, all I have is inside is 1 squared plus 2 zeta beta the whole squared square root. Okay. So, therefore, if you look at this, the Bayes isolation parameter then becomes, and what is d? D is square root of 1. So, I am going to rewrite this. So, what does this become? 1 plus 2 xi beta the whole squared upon 1 minus beta squared plus, that is d, and the, so under square. So, you see I have multiplied this with d. D is 1 upon square root of 1 minus beta squared the whole squared plus 2 xi beta squared. Okay. So, I have just put it inside the square root, and if I put it inside the square root, this is what I get. And note, look at this. What is this? This is the same as the transmissibility ratio, which was f t 0 upon f 0. Two totally dissimilar problems, absolutely dissimilar problems. One is a force transmissibility problem, the other is transmission of Bayes acceleration to the equipment acceleration. So, this is a Bayes isolation problem. We are trying to isolate the Bayes vibration transferring on to the equipment or whatever, any other, I am calling it equipment for want of anything else. And the other one is essentially transmission of a force from a machinery to the base. Okay. So, one is force transmissibility, other is acceleration transmissibility. But note that mathematically both give us the same transmissibility ratio, which is what is given in here, which I had looked at yesterday in terms of force transmissibility, and today the same equation again is valid. So, again if I want to look at the situation where I want to isolate, I have a sensitive equipment and it is connected through a foundation to the floor, and now the whole problem is design of the Bayes isolation system. Okay. So, that this u g 0 amplitude and this u total amplitude, in other words, this acceleration that this Bayes is being subjected to, the Bayes is isolated, the equipment Bayes is isolated from the floor. So, this is a Bayes isolation problem, and essentially what we are saying is this is the same as the transmissibility ratio, which is 1 plus 2 xi beta upon 1 minus beta squared plus 2 xi beta the whole squared under square root. So, this is the design of the Bayes isolation. So, I have to design K and C such that the transmissibility ratio tends to 0. That is my design problem. Let us look at this thing. Again, where do you get transmissibility ratio 0? You get it when beta is very large and xi equal to 0, because the lower the xi, the faster it goes to 0. So, therefore, again the same thing. And what does beta equal to 0 imply? Let us look at the same problem. Omega bar is fixed. So, beta large means low omega. Low omega means flexible spring. You see, the force transmissibility problem and the Bayes isolation problem are identical. Okay? And therefore, both of them essentially are looking at, if you want to design an ideal force transmission to be 0 or Bayes to be completely isolated. In other words, acceleration transmitted from the ground to the equipment or force from the equipment to the ground, both of them essentially require a flexible system. Again, again the same thing. Here is the equipment. The Bayes is able to move. The Bayes is moving. If the Bayes is moving, okay, if you have a flexible thing, this does not feel it. Think, okay, I mean, think from your personal experience. Okay, if you are driving a Maruti car on a very bumpy road, okay, and on the other hand, you have a Mercedes Benz, okay, where do you feel more comfortable? You feel more comfortable in a Mercedes. Why? Because it has extremely flexible shock absorber systems. So, what happens is, if you actually look at a Mercedes going on the road, you will see that the car goes like this and the wheel just keeps going up and down, because the shock absorber is essentially a very flexible spring which continues. So, this is exactly the problem that we have solved, and we have shown that mathematically both the problems are identical and they essentially come around the concept of the transmissibility ratio. Okay. So let us look at a couple of problems to see how we can solve this particular issue. So, let me look at a particular problem, and let me take a problem that I have. I have machinery whose weight is, note that typically we say weight is 2 tons, it is wrong, okay, because weight is a force, and in SI units force is always kilonewtons. So, let us say that weight is 20 kilonewtons, okay, and the excitation that we have is, this force is transmitting a force, it is operating this what should we say, the equipment is operating at 1500 revolutions per minute. Okay. So, and it is transmitting a force. The weight is not the force, by the way, because the weight is a constant weight which exists, okay, but it is transmitting a force of amplitude equal to, say, 2 kilonewtons, okay, and this is a vertical force being transmitted, okay, and we have to design K and C such that we reduce this, the force transmitted here, to as low a value as possible. This is our design problem. Okay. So, I have a rotating machinery operating with weight whose weight is 20 kilonewtons. it's operating at 1500 RPM, and because of some eccentricities in this rotating machinery, it's actually subjecting, it's actually transmitting a force whose amplitude is given by 2 kilonewtons. Okay? Okay. So, this is the force that is being transmitted. And by the way, this is a harmonic. We know that this is a harmonic force. Why? How do we know it is a harmonic force? Well, it is moving at a constant RPM. What does 1500 revolutions per minute mean? Well, let us put it, divide by 60, what do you get? 25 revolutions per second. Revolutions per second means every 1/25th of a second, the force goes round and comes back to 0. In other words, the omega bar is equal to 25 into 2 pi radians per second, because every one circle is 25 radians. So, omega bar, the excitation frequency, is equal to 50 pi radians per second. Okay? So, therefore, we know the excitation frequency, we know F0, and so therefore, what we need to do now is look at the possibility of transmitting as low, and let us put it this way. I am going to say that, look, this is going to be point maximum that the ground can, this floor can take is 0.2 kilonewtons. Okay? The maximum amplitude that I have is 0.2 kilonewtons. That is what I am given. Okay? So, this is the load coming, this is the maximum force that can be transmitted to the floor safely. Okay. So, how do I solve this problem? The problem is find K, find C. Okay. Now, let us look at transmissibility. Transmissibility becomes 0.1. Okay. So, transmissibility 0.1. In other words, transmissibility cannot exceed 0.1. If it can't exceed 0.1, what happens? If you look at it, if it can't exceed 0.1, that means this is the value. So, we come here. Okay. That means we are in this zone. If we are in this zone, we have beta greater than 0.2, and if beta is greater than 0.2, we know that the lower the damping, the better it is. So, in other words, xi is equal to 0. So, in other words, this implies that C is equal to 0 automatically, okay, because if xi is equal to 0, C is equal to 0. So, it is an undamped system. So, if it is undamped, transmissibility ratio is given by what? Let us see what the transmissibility ratio becomes. It becomes 1 upon the plus 2 xi beta, xi is 0, so that disappears. Then we have 1 minus beta squared plus 2 xi beta, that disappears. This is square root. So, this becomes 1 upon 1 minus beta squared plus or minus. Remember that when you do this squared and then you do the square root, okay, the square root is not necessarily 1 minus beta squared. Okay. It is plus minus 1 minus beta squared, whichever value is needed to get us to get a realistic picture. Okay. So, in other words, if I look at this, what do I get? I put this equal to, so that I get, so if you look 1 minus beta squared is equal to 10, it basically means it is beta squared minus 1, which is 10. Okay. So, that means it is a minus that works, and so therefore, beta squared works out to be 11. If beta squared is 11, beta is equal to root 11. Okay? So, beta is root 11. What does that mean? Let us look at it. Okay? Beta is equal to root 11 implies that omega bar upon omega is equal to root 11. Again, I want to find out omega squared, because omega squared is equal to k by m, which is equal to, if you look at it, it is equal to omega bar squared upon 11, and omega bar squared, omega bar is 50 pi. Okay, so this squared, right, and this upon 11 is equal to k upon m. Now, what is m? We have given weight is equal to 20 kilonewtons. If g is, I normally take it as 10 meters per second squared, is actually 9.81, but for our practical purposes I can take it as 10. Okay, it just makes life simpler. Mass then is equal to 2 tons or 2000 kg. Okay, mass is 2000 kg, then k becomes equal to 50 pi squared upon 11 into 2000, and the units of this, since this is kg and these are radians per second, this becomes Newton per meter. That is my k value. Well, you know, you can get the value. It doesn't really matter what this value is. It's, you know, if you look at it, you will see that this becomes kilonewton per meter, okay, and this is 2500, 5000 pi squared. So, k is equal to 5000 pi squared upon 11 kilonewton per meter. You know, it seems, you know, we talked about the fact that this looks, you know, this seems very soft, okay, but note that, you know, despite the fact that to get a transmissibility ratio of 0.1, okay, we see that it is 5000 kilonewton per meter. So, let us now look at under the weight what kind of displacement do I get? I mean, what kind of travel do I minimum require? The minimum travel required is, well, weight upon k. So, that is equal to 20 kilonewtons divided by, so into 11 into 5000 pi squared. Okay. Pi squared is approximately about 10, you know, I mean, I can take it as 10. You can do a much better computation if you want to do it. I can take it as 10 for this particular purpose. And so, if you look at it, this goes, so this becomes 4.4 into 10 to the power of minus 3 meter, which essentially means approximately 4.4 millimeter. Okay? That is not a very soft spring. Huh? A 2-ton mass is only transmitting 4.4 millimeters. So, you see, when we talked about, when we were talking about that we require soft springs, and you know, I was saying that sometimes soft springs cannot be provided because they become, you see, I went through the computations to show you that even to get a transmissibility ratio of 1/10, okay, which is like, you know, 0.2 kilonewton. When you have a 2 kilonewton force, it is 0.2 kilonewton. It is practically negligible. You know, the transmission is very, very low. Okay. Even then, you get k, which with a load of 20 kilonewtons, okay, which is equivalent to a mass of 2 tons. Okay. What you get is 4.4 millimeter travel. fairly stiff springs, right? But those stiff springs are enough to ensure that the force from the machinery is not transmitted to the foundation. And this, where do we see this? This is typically in real life in designing a turbo generator foundation, a turbo generator in any power plant, a turbo generator design of the foundation. This is the procedure that you go through. First, you want to ensure that there is no resonance, and for that you have to ensure that your K is soft enough, and soft enough is not really soft, it's fairly stiff, but even that stiff one is good enough for us to ensure that we have this. Okay. So, that is a problem of force transmissibility. Now, let me look at a problem of base isolation, and for a base isolation I will take a practical problem. A practical problem with a slight twist in it, just to ensure that we get a harmonic harmonic kind of excitation, purely because we have studied harmonic. Later on, when we study more complex thing, the same concept can be applied equally well for more complex kind of situation. So, let us see what the problem that I have. You see, because of foundation settlement, let me look at this particular problem. What I have is a bridge, okay, which, because the foundation settle, it becomes something like this. So, the surface of the road, which should have been straight, okay, because of the settlement of the foundation, okay, now becomes a wavy. This is something that all of you have experienced when you have driven anywhere. So, I am actually kind of just taking a problem from real life with a little bit of assumptions to make it tractable right now. So, I will call this that. So, the road surface, okay, the road surface is essentially, because from this to this is 10 millimeter, and we will say that therefore, the base, which is the ground, can be given by UG0 sin omega bar t, where UG0 is not 10 millimeter, 10 millimeters from the bottom to the top, peak to peak. So, therefore, note that the UG0 is half of that. So, that is equal to 5 millimeter sin omega bar t. That is my problem. Okay? And what I have is, I am sitting in a car, and for now let me just assume that it is one wheel, just to make it simple, it is one wheel, and the shock absorber system has K and C, and the total mass of the vehicle and its occupants are given by m. Okay? And what I want to know is, I am an occupant in the car. What do I want to see? I do not want to be accelerated. So, in other words, the problem is that I do not want to feel too much this, I want to reduce this to the bare minimum that I can. Okay? So, this is a practical problem that we have. We have defined the problem. Now, the question here, what is the question? The question is, well, the car is moving at a particular velocity. Okay? And the other thing is that this distance is, let us say, 40 meters. The spacing between the two piers. What does that give me? Can anyone tell me what that gives me? That gives me that if I look at this surface, okay, if you look at this is not the kind of surface that we are defining here. It is not T, it is with x. Okay. So, if I look at it, this is going to be equal to something called lambda x, where x is what? x is this. Okay. And what is lambda? Lambda is what is known as the wavelength. In other words, one wave, this is a wave, right? One wave, what is the length from one wave to another wave? See, this is the bottom, this is the bottom again. So, from bottom to bottom, or you can look at it, bottom to bottom is nothing but one cycle. So, I am looking at the wavelength is really one cycle of the wave and the distance. So, gamma over here is actually lambda is 40 meters. Okay. And this car is moving with a velocity v. Okay. So, I have defined all the problems. Okay. This is moving at the velocity, and the whole issue of this particular problem is finding out the shock absorber system of the car, the properties of the shock absorber system. So, let us look at it. So, how do I solve this problem? Well, I have taken this problem and written it as a wave in space. How do I transmit that wave in space into a motion of the wheel? Well, let us look at it. Let us say that this car is moving, the velocity of the car is 72 kilometers per hour. Okay? Then my question becomes, how long, when it is traveling at 72 kilometers per hour, okay, I can transfer 72 kilometers per hour into meters per second. How much is that? 72 into 1000 becomes meters per hour, and there are 3600 seconds. So, this becomes how much? 20 meters per second. So, in other words, this car is traveling at 20 meters per second. So, now let us look at it. How long is this car going to take going from here to here? It is 40 meters, it is traveling at 20 meters per second, it is going to take 2 seconds. So, in other words, the time to go through one cycle, the time required to go through one cycle is how much? 2 seconds. And this becomes, so this becomes then the excitation, because in other words, the wheel every 2 seconds is going to go from here to here to here, and that is a sign. So, in other words, what have we done? We have transformed this problem into a problem with omega bar t. Okay? And what is that equal to? Because we know that it is traveling at 20 meters per second, it takes 2 seconds. So, if it takes 2 seconds, that means what is the frequency? It is 0.5 hertz. And what is the excitation frequency then? 0.5 into 2 pi. So, that is pi radians per second. That is my omega bar. Okay? So, that is my omega bar. So, in other words, I can now say that this UG is can be written as UG0 into sine pi t. Is that okay? So, now the question is, this is the displacement. Now, remember we were looking at acceleration. So, I have to find out the acceleration. What is the acceleration going to be equal to? It is going to be equal to, we have gone through this many times. So, I am just going to write it down. It is going to be UG0 pi squared minus sine pi t. 9 is because you double differentiate it. So, this then becomes my, and this is 5 millimeter. So, 5 millimeter becomes 5 into 10 to the power of minus 3. This is approximately 10. So, this is 0.05 meters per second squared. So, therefore, u double dot z 0 is equal to, this is 10, 5 millimeter in meters is 5 into 10 to the power of 3, 15 to 10 to the power of minus 3 is 0.05 meters per second squared. This is the amplitude of my acceleration. Okay? So, if this is my acceleration, then how do I solve this problem? Well, again, what I need to do is, I have now, you see, I have taken that particular problem and made it into a problem that I can solve. Okay? So, my problem then becomes this, and I know that this is equal to okay. So, the question becomes that, again I say that this is a transmissibility ratio, and I want to say that, look, I don't want, I as a car person, I do not wish to feel anything more than 0.005 meters per second squared. That is the maximum that is comfortable. Automatically TR becomes 1 upon 10, and we go through the same steps. Note that if TR is 1 upon 10, xi has to be equal to 0. If xi has to be equal to 0, then what does TR is equal to 1 upon minus 1 minus beta. In other words, 1 upon beta squared minus 1, which is equal to 1 upon 10. So, beta squared is equal to 11, and beta squared is nothing but omega bar upon omega squared is equal to 11. So, again omega squared is equal to omega bar squared upon 11. Omega bar is what? Remember? Omega bar was pi, so that is pi squared upon 11. So, essentially this is k upon m. Again, what do you get? You have a situation where omega squared, which is k upon m, is equal to pi squared upon 11. Now, let me take that as approximately 1 for all practical purposes. Basically, that means k is equal to 1 into m. What was the mass that we had said? The mass of the car? The mass of the car we had not given. We will take the mass of the car as 2000 kgs. Okay. So, therefore, k is equal to 2000 Newton per meter. Now, this is a very, very soft spring, because this is going to give rise to huge displacements which we can't take. Okay. So, in other words, designing this shock absorber, understand this, that if this is k, weight is what? Weight will be 20 kilonewtons. Okay. So, therefore, if weight is 20 kilonewtons, this is 2 kilonewton per meter. What is my displacement? 10 meters under the load. Impossible, right? So, this is not possible. This problem, in other words, we have discovered that, look, under the weight, the spring will have to go 10 meters. And if the spring has to go 10 meters, then obviously we have a basic problem. The problem becomes that if I am going at 72 kilometers per hour and this is 40 meters, okay, we have a problem. However, let us look at the problem. Let us see if this 40 meters was made into 2 meters. In other words, you are going at still the same speed. You are going, look at it. See, understand one thing, that you have a situation where your system is being subjected to very slowly varying, and we see that the design that we have, it's practically impossible to do the design for that. Now let's look at, let's take, it's a road surface, let's not take a bridge, it's a road surface, and road surface is very rough, very rough. So in other words, I have 5 millimeters and the spacing is 2 meters. In other words, it's a very, very rough road. Every 2 meters, if I have this kind of a thing, and this is my 5 millimeter, think of how rough a road it is, right? Very rough road, right? Let's look at something very interesting. If it's this, then how long does it take to travel? If it's still traveling at 72 kilometers an hour, T prime becomes 2 upon 20. It takes 0.1 second. So F prime becomes 10 hertz. Omega bar becomes 20 pi radians per second. Okay. We still have that same problem. In other words, I still want the 1/10, right? So I still have the same thing where omega bar is equal to omega bar squared. Now omega bar squared is what? So omega squared is equal to 20 pi the whole squared upon 11. So that is like 400 pi squared upon 11, which I will take it to be 400, which is k by m, right? And if you look at this k by m, then so k is 400 times m, which is 400 into 2000. Okay, so this becomes 800 kilonewton per meter under the load of 20 kilonewton upon 800 kilonewton. How much does this go? 1/40th of a meter. 1/40th of a meter is equal to 25 millimeter, which is doable, 2.5 centimeter. Okay, this is a viable shock absorber system. In other words, this is a very, very interesting problem. The interesting problem is, I am traveling at 72 kilometers per hour in a car. Okay, if it is on a bridge which is 40 meters span and it is moving, it is going to feel, because I cannot design it, you saw that I can't design it. So it automatically means the whole entire road surface is going to be felt here. Okay. However, as soon as I took the problem and made it into a very rough surface and I am going really fast, what happens? I can design this car now. The same people who were feeling the entire acceleration in a very slow wavy road, now in a rough road, if you are traveling at 72 kilometers an hour, what happens? You don't feel it at all. You see how interesting the problem is? What's happening? What's happening is that you are moving so fast that the car does not, in other words the mass, you yourself sitting in the car, does not even realize that it is being subjected to a vibration. Whereas when it is slow, what does it become? It becomes almost like a static load. So it feels the entire acceleration comes into the car. So this is a very interesting. Of course, it's not. One is not talking about what the tire is going to, what's going to happen to the tire. I'm looking purely at a personal comfort, and a personal comfort is much easier in a very, bad road on a very flexible Mercedes than it is if a Mercedes is going at 72 kilometers per hour on a wavy bridge. Okay. So, this is a very interesting problem, and we will talk more about this as we move along. Thank you very much. Bye.